Rate of reaction. Now what is rate of reaction? Rate of reaction is the change in the concentration. So I'll write this here, it's the change in concentration, and concentration we label this as the indicator for concentration. So I'll just put here change in concentration of the product, or change in concentration of the reactant. So I'm just going to put this again, bracket for concentration, so or the concentration of the reactant per unit of time. So I'm just going to put this all per unit of time. And this whole thing is usually measured in moles per liter, because we know moles per liter is concentration. So this here is going to be in moles per liter, or you could do it this way, right? It's the same thing, per. However, so this is per, right? However, it also has per unit of time as well, so we have to put it in seconds there as well, okay? And this technically is the same as moles per liter multiplied by seconds, in case you're still confused as to why. If you just do simple factorial analysis, so if you have moles per liter over here, and you just, again, divide it by seconds, you could just divide it by seconds this way. And when you have it done this way, technically everything's over 1, so this is all over 1. You now have two fractions, and you have a divide symbol in between. So what you can do here is just do moles per liter, and then this divide symbol just goes away. You just change it into multiplication. Then you obviously got to flip this one, right? This one goes up, and then this one goes down. So now you have 1 over the S. Okay, and then all you need to do is just multiply the numerators and then multiply the denominators respectively. So then you have mole times 1, which is just mole, and then you have moles, and sorry, then you have liters times the seconds on the bottom. That's how you end up getting this one over here. Okay, so now let's move on to another one, average rate formula. So I'll just put AVG for average. Okay, so now we have the average rate formula, which is the change in concentration. Okay, so obviously change is going to be represented by delta always, so we have change in concentration. Okay, for something over here, we don't know what it is, we're just going to indicate it as C. Okay, and then it's a change in the time. Okay, so T here is going to be represented as time. So this can also be expanded in a way where you have the concentration of that particular substance in question, and that's going to be C, but I'm just going to put a small final here, okay, because this is the final. Okay, and then I'm going to do the same thing for the initial. It's going to be represented as such. Okay, so we just do final minus the initial, and then we're going to do the same thing for the change in time as well, right? Because time also has a time final, and then there's also going to be a time initial. Okay, so this here is the formula for the average rate. Now, this is very different than the instantaneous rate. So for the instantaneous rate, it's the rate at any given point in time. So I'll just write here, rate at any given point in time. Okay, so we don't really necessarily need to be doing this. We can create a timeline, and then we just write our concentration and just jot it down at the particular time, right? So if we have a time scale here, okay, and it just increases going this way, whatever the time is, let's say 5 minutes or 6 minute mark, okay, let's say that's like right here, we just write down the actual concentration, because instantaneous rate is only at a particular time. Okay, sometimes you don't even need to be using the time at all, because if it's instantaneous, you're not trying to look for a range between the 2 points, so sometimes you wouldn't even use the time, because you already know if it's referencing this one over here at, let's say, a 6 minute mark, that's all we really need. We just need to know the concentration. You don't need to know that the time is at 6 minutes, because it's instantaneous anyway. Whereas an average rate, if you have 2 markers over here, you would have to know the times between the 2, because you have to get the difference between the 2, right? You have to know the final and then the initial. For the instantaneous, it's just 1 time, so sometimes we don't even need to use that. By the way, rate is always represented as a positive value, so I'll put this here. Okay, rate is always, I'll just put RAP for rep. Okay, it's always represented as a positive value. This here is positive, okay, as a positive value, regardless of concentration, okay, increasing or decreasing over time. Okay, so just keep that in mind. All right, so I'm just going to put here on the side that the choice of the method to be used when we measure the rate. Okay, so the methods, so maybe I'll write here the methods, okay, to measure the rate of the reaction. Okay, so I'll just add that over there on the side. The choice of method to be used depends which reactant or product is measurable. So I'm just going to write this here on the side. Okay, choice of method to be used depends on which reactant or product is measurable, okay, or is to be used. So for example, we'll just look at our first one over here. It will be an indicator through the lens of color change. Now, when would we be using this one? So when a reactant is completely used up or reacted, it's going to change color. And in that case, for us to see the rate of the reaction, to be able to measure that, obviously the best thing to be using is a spectrophotometer. Okay, so I'm just going to put here in brackets, an example would be a spectrophotometer. Okay, and why would we be using that one? Because it measures the absorbance of light at any wavelength. So of course, color here would be a visible light wavelength. So of course, that's going to be optimal to be using for this setting. Okay, so a spectrophotometer, it measures the absorbance of light. Now, that is for color change. What we can also measure is when there is a change in pressure. Okay, so maybe I'll just put here delta for change, okay, change in pressure. Now, if that's the case, this is only for gases, okay? Only for gases. Now, if there is an increase in the amount of moles, what's going to happen to the pressure? You guessed it, it's obviously going to increase the pressure. What happens when you increase the pressure? Then of course the reaction is going to proceed, okay? It's going to proceed to the right, okay? If we usually put our yield symbol this way, okay, it's going to proceed to the right. So I'll just write this one over here, an increase in mole, or the amount of moles, so I'll just put amount, an increase in the amount of moles okay, is equal to an increase in the pressure. And then what's going to happen there? It's going to increase the reaction to proceed to the right. Sorry, not increase the reaction rate, increase the reaction to proceed. To the right, okay, to the right. So that's the second indicator, okay, if that would be optimal. Another choice of an option we have is if you see a precipitate forming. So we can put a precipitate here, precipitate forming. So if a precipitate forms, if there is more precipitate forming as time goes by, this is going to be quite easy to measure, right? So for example, if we have, okay, let's say we have like a tube over here and we have precipitate forming over here, okay, for a particular amount of time, and then the next second we have another one, so we with the same one, okay, but instead of it being here, now it has increased to here, okay, we get the same one here, okay, and then after more time has gone by, let's say it's now up to here, and it just keeps increasing as time goes by. So precipitate forming as time goes by is an easy way also for us to measure how much it has increased. So that is the precipitate formula, okay? We can also look at another one here, would be a change in conductivity, okay? So I'll just put this here, change in conductivity. Okay, now what does this mean? Well, for conductivity to occur, of course we need to have ions in place, right? Because they can't be, covalently bonded, right? It can't be, it can't be done that way, because then there's no free electrons floating around in the sea, right? It has to be within the ions, right? So the if the ions are broken apart, okay, now the electrons can go from one ion to the next, which would increase the conductivity. Okay, if there's no ions around, right? So if, for example, if something is like ionically bonded, then of course it's not going to be able to conduct electricity unless you break it apart. So something like water would do a very, very good job at breaking apart that ionic bond. Now you have two ions. You have the cation and then you have the anion. So now we have a free floating amount of electrons that can move around, okay? So I'm just going to put here change in conductivity, okay, in brackets here, as the ions increase, conductivity increases too. Okay, so the more ions that dissociate, the more conductive it's going to be, because now there is more for the electrons to go around, right, the sea. All right, number 5, we have a change in pH. This is also a way to measure. Okay, and how do we do this? Well, the pH is either going to increase or decrease as the reaction progresses, so we can obviously measure how the pH is going to be changing. If it's going to increase, so it's going to become more basic, or if it's going to decrease and it's going to become more acidic on the pH scale. Okay, and there's obviously different tools that we can use in order to measure that change, whether it's through indicators, litmus paper, a pH paper, etc. Okay, so we have an will increase or decrease as reaction progresses. So these are the different methods that we can be using. Now let's look at a few introduction questions. What type of data could be used to determine the rate of the reaction for the chemical change that occurs when acid rain dissolves the limestone? Okay, so limestone is just calcium carbonate. You all hopefully should know that. So that's CaCO3. So CaCO3, okay, and obviously this is going to be in a solid form, and then there's acid rain, okay, so there's acid rain, and it's going to start breaking it apart, it's going to dissociate, okay, and then it's going to release, let's say, CO2 as one of the products, okay, and obviously, calcium needs to be here as well, and then it's probably some water too, because it's going to be dissociating with the acid. But let's just look at the CO here, the CO2 that is dissociating. Let's just focus only on that compound, and obviously it's going to be gaseous, right? So it's going to release carbon dioxide. Which method are we going to be using? So just pause the video, think about it. Based on what you looked at, you can kind of go back on the video if you've paused it by now, and then you can, rewind a little bit and then see out of the 5 which one are you going to be using. All right, so hopefully you've had time to double check. All right, the thing we're going to be using is the change in pressure. Okay, so if we have the CO2, it's going to be increasing, right? So if there's an increase, okay, in the gas, right, the amount of moles of that CO2, okay, so let's just say increase the moles here, what's going to happen? Well, it's obviously going to increase the pressure. So if we can confine that and measure that, that would be ideal. So if it increases the pressure, right, then it's obviously just going to increase the rate, increase the reaction to proceed. Okay, and obviously we could also check to make sure that the CaCO3, what's going to occur based on the law of conservation of mass, right? This one here, do you think it's going to stay at the same mass, right? So what's going to happen to the mass? Is it going to increase? Is it going to decrease? Of course it's going to decrease, right? So the mass should decrease as well. So you should be able to obviously measure that quite easily, right? So the mass should decrease because more CO2 is being released as one of the products. So this is the method that we're going to be using, method number 2. To determine the average rate of a chemical reaction, okay, we're looking for average rate, right? So what's the first thing that we're going to be doing? We're going to be writing out the average rate, okay, formula. You know, I love to use formulas stated at the very beginning, so we could always reference that on the side. So we have average rate here, again, is a change in C, or the concentration of that, okay, over the change in time. Okay, so we're going to be using that. Okay, a technician determined that the concentration of a substance was 0.25, okay, at this amount of time, and then as we go along at 2 minutes, you now see it at 0.420 moles per liter. So what is going to be the final? Okay, obviously it's going to be 0.420. This is the final one, whereas this here is going to be the initial one. So I'm just going to write it out as such. So I'm just going to put the average rate here, and for the concentration, okay, this moles per liter here, so I'm just going to put 0.420 moles per liter. And I need to subtract it by this initial, right, concentration, as indicated here, right, final minus initial. So we have 0.25, okay, so we have 0.25 moles per liter. And then this is all going to divide by what? We have a certain amount of minutes involved. We have 2 minutes, so that was the final that we're looking at. So we're just going to put 2 minutes over here, and it's subtracting by the 0.5 minutes. I'm just going to put that over here. Okay, so all I'm going to be doing is subtracting this. Okay, so again, you can actually change this 2 minutes and change the 0.5 minutes into seconds anyway, because we like to use seconds, right? Moles per liter per second. Okay, so obviously the 2 minutes over here, you can obviously just do this in your head, but I like to scaffold it for those who need it. Okay, so for the 2 minutes over here, obviously we don't want minutes, right? So technically 2 minutes is the same as 2 minutes over 1. Always multiply a fraction when you want to figure out your conversions. Okay, so now we have 2 fractions involved, and then obviously what do we want to get rid of? We want to get rid of our minutes, right? So I'm going to be putting my minutes on the bottom. What do I want? I want seconds, right? So I want seconds to be on top. Remember, these are proportionally associated with one another, so we have to make them the same though, right? So if there's 1 minute involved, right, how many seconds are there? There is 60 seconds. Okay, so obviously the minutes and minutes, they cancel out diagonally because of the same unit. Everything else just multiplies. You got 2 times 60. Okay, so you got 120, and you're going to put that into seconds. All right, so I can actually just change this 2 minutes over here into the seconds. So I'm just going to erase this and then put 120 seconds. Okay, the same thing can be done for the 0.5, okay, so 0.5 minutes, and then I'm going to multiply by a fraction. Technically this is over 1, and then of course I want minutes on the bottom, so I want to cancel those out appropriately, and then there's 60 seconds, okay, for the minute, so you just get 0.5 times 60, so then that's obviously just 30, okay, so you just get 30 seconds. And I'm just going to use my calculator here, 0.420 minus 0.25, and I'm getting 0.17 per liter. Okay, in terms of the seconds, we can just, obviously that's easy, right? We have 90 seconds, so all we're going to be doing now is dividing this so that we get moles per liter per second. Okay, right now we only have 90 seconds. We obviously want just 1 second, so you're just going to divide them, and then you end up getting 1.888. Okay, times 10 to the negative 3, okay, moles, okay, per liter, okay, per second over here. Okay, and you notice how this here is in a positive value. Okay, obviously everything is going to be in positive anyway, right, when we're going to be putting them as a conclusive statement. But obviously here, when you do the orders appropriately for the final minus the initial, this is for sure 100% positive. Okay, this means, was the technician using the reactant or product to measure the rate of the reaction? Obviously it has to be the product. Okay, so the answer has to be the product. Okay, because obviously it has been increasing as it went along, right? This means more product was being formed because it was increasing in number. So the answer here would be the product. Alright, so let's look at this question over here. The reaction shown below, average rate of formation of CO2 is that many moles per second. What amount of moles of CO2 is formed in 5 minutes? Okay, so we're still looking at CO2 over here, and because that's what they give us in the question, but the question after that, okay, is asking for the CO2 again anyway, but not at this amount of seconds. We're trying to figure it out in 5 minutes time. So how do we do this? Well, we're just going to obviously change this into the seconds, because we always want to be dealing with the seconds, right? Because that's the unit that we've been covering so far. So let's keep it at that standard, keep it consistent. So moles per liter per second. So we're just focusing and centering around the second, not the minutes. So we have the 5 minutes over here, and I want to change it into seconds. Same thing. I'm just going to put my minutes down here, and then I want my seconds on the top. what's going to happen? Our minutes and minutes cancels out. So now obviously what do we end up getting? Right, 65, 30, and then you just add that 0 over there. Now we have 300 seconds. So what are we going to be doing now? Well, we have this much, 5.5 times 10 to the negative 4 moles. And then this is obviously per second. The thing is, we want 300 seconds. So how is that going to become? Well, again, we want our seconds to cancel out because we're just solely trying to figure out the moles. Okay, so I want my moles here to be remaining, and I don't need the seconds anymore. Okay, so I have 300 seconds. I'm just going to cancel out these. So then what do I end up getting? Just use your calculator. I end up getting 0.165 moles. Okay, so this is covering over 300 seconds, so it's quite of a long time. Okay, so I have 0.165 moles. Okay, and this is all over 300 seconds. Okay, now this is for CO2, but how does this compare with the next question for Br2? Well, whenever we're trying to find the proportionate amounts between two different coefficients of the compound, so again we have CO2 over here, which we're done, but now we're trying to figure out Br2. So what is the coefficient in front of Br2? It's also 1, right? So there's 1 over here, and then there's 1 mole over there as well. So whenever we try to compare between the different reactants or the products in the actual equation, right, the balanced equation, we're just gonna all, based on our unit, divide it all by the coefficient in question. So for CO2 we only have 1, so I'm just going to put 1 over here. Okay, and then from there I also want to make sure that it's going to be equal to, so you know what, I can get rid of these equal signs over here. I'm just going to put the equal sign over here, and it's going to be equal to our BR, okay, our BR2 over here. Okay, so my BR2 is going to be listed over here, and again this has to be in the amount of moles. Okay, and I don't have a time over here that I need to use, so I'm just going to be putting over 1. Okay, now in terms of the coefficient is 1, right, because there's only 1 mole over here, so I'm just going to be putting 1 over there. Okay, all you need to do whenever there is an equal sign in between and you have the fractions, all you need to do is multiply them diagonally. This is always going to be the case. So I'm going to first multiply my 1 times the BR2. Okay, so that's obviously just BR2, so I only have BR2. Okay, and then the next side is going to be this, right? This 0.165 moles per 300 seconds. This needs to start now multiplying with this one. Okay, so we have this 0.165 moles per 300 seconds, and you need to multiply by this 1 over here. Okay, obviously that's going to be the same. So technically what we have for the BR2 is this, right? It's the same thing, 0.165 moles per 300 seconds. So this here would be the answer. Concentration of a reactant is that many moles per liter at 2 minutes. If the average rate of consumption of the reactant from 1.5 minutes to 2 minutes was that rate, what was the concentration of this reactant at 1.5 minutes? Okay, so this is a lot of different times of, a lot of different points of time involved. So what could actually we do? We should make a little timeline here to make it a little bit easier for us. Okay, so again we have about 0 minutes over here, and then we could have like 0.5 over here, then we could have like 1 over here, then we could have like 1.5 here, and then we can have like 2 here, and then 2.5, and then like 3. Okay, so I'll just label it appropriately. So this is 0.5 minutes. Again, all of this, let's just say it's in minutes. So 0.5, and then this is like 1.0, and then 1.5, and then 2.0, and then 2.5, and then 3.0, and then we just have to start pinpointing, like I said at the beginning of this video, where needed. Okay, so we have this 2-minute marker right over here. Okay, it's going to be our 4 times 10 to the negative 2 moles per liter. So 4 times 10 to the negative 2, okay, moles per liter of concentration. Next, if the average rate of consumption of the reactant from 1.5 minutes, so this one over here, to this 2-minute mark was 0.45, okay, 0.45, so this is going to be 0.045 moles per liter, okay, per second. So this here is the rate, whereas this one here is the concentration. Okay, what was the concentration of this reactant at 1.5 minutes? So this here is our question. Okay, in terms of the concentration, I'm just going to put concentration there. Okay, what is this going to be? Well, we have to start looking at it. What changed, okay? Because what changed in terms of the rate between here, because if there was a certain amount that we know of 0.5 minute difference, so if we knew 0.5 minute difference, what the change was in that 0.5 minute time slot, which is 30 seconds, right? So what happened in this 30-second time slot in terms of an increase or a decrease, we can literally just add that on top of this one, and then we can figure out what it was before that, okay? Because it used to be a certain amount over here, and then it changed, and then it became this concentration later on. So the problem right now, though, is this 0.045, right? Whatever happened here, it's not based on what happened at 30 seconds. It's unfortunately, this shows what happens only per second. So we got to figure out what changed, okay? What this value really was in 30 seconds timeline, okay? That 0.5 minute timeline, as opposed to just by the second, because the second here is useless to us. We have to find out the difference between here, the two, and then add that on top of what it's now become, so that we can figure out what it was before that. So this seconds here, again, is useless to us. We got to figure out what it is, okay, in terms of the 30 seconds. So we have this 0.045 moles per liter, okay? And again, this is, okay, maybe I'll just change this here, moles per liter, okay, per second. We are trying to figure it out in the 30 seconds, okay? Because this is 0.5 minutes, which is same as 30 seconds. So I need to change this into 30 seconds. So then obviously, it's technically over 1, right? So this seconds cancels out. So what do you end up getting? End up getting 1.35. 1.35 moles, okay, per liter. All right? So this is what's technically happened, okay, within that 30-second timeline. So if that's occurred over here, what was it before? Well, we'll just put our little question mark over here. And as you can see, it used to be a certain amount, and then it decreased into this amount. All right? So what was it before? Well, we're trying to figure that out. So then if it decreased by whatever this value was, right, within that 30-second time slot between here, so we can put that over here, 1.35 moles, okay, per liter, and then it eventually became this 4 times 10 to the negative 2 moles per liter. We're just going to do some simple algebra, right? So then this one over here is obviously just put plus 1.35. Maybe I'll just squeeze that in here. Okay, you got a plus 1.35. Okay, moles per liter. You do it on the left side. You got to do it on the right side. So you get plus 1.35 moles per liter. So then these cancels out. So you're just left with this one. So your answer here would just be 1.39. I'm getting 1.39 moles per liter. That here is your answer. Zinc electrode immersed in this temperature over here. We have this balanced chemical equation. The volume of H2 present at 1 minute is 30 mils. Notice how it's in milliliters now, okay? It's not just giving us a concentration, which is fine. We can still work with it. And then we have 1.4 minutes a little bit after, and then now it's increased to that much, okay? What is the average rate of formation? Okay, this should be quite simple. We have the average rate formula like we always do, okay? It's going to obviously equal the change of concentration, C, okay, over the delta T. Now, our final over here versus the initial over here, we're going to add that in. So we're going to have, again, average rate is going to be our final. Okay, I know it's not a concentration, right? It's just a volume, but it's okay. We can still work with it, 42 mils. We're going to subtract it by the initial. Okay, so this was the final. Now we're going to work with the initial here. This is 30 mils. And then this is all over the certain amount of time difference. Okay, so we have final time minus the initial time. What are we going to be doing next? Well, this one here should be simple. That's just 12, okay, milliliters. Now, what are we going to be doing down here? This is just going to be 0.4 minutes, okay? Are we done? No. The question is saying, what is the average rate of formation of H2, okay, over this period of time measured in liters per second? Okay, we don't have liters per second right now, so we got to change this milliliters into the liters. So rather than this milliliters over here, we have to make this into liters, so that's just 3, all right, backwards. So we got 1, 2, 3. Because we're just going to add a 0 in there. So this is going to be 0.012 liters. Okay, so 0.012 liters. Okay, and then we have our 0.4 minutes over here. There's 0.4 minutes. Now, do we want to keep this in minutes? No. We obviously want to change this into the seconds. We have to multiply by, again, our factorial analysis method. We have 1 minute up here. It's got to be same down here. So instead of 1 minute, it's going to be the same as 60 seconds. So obviously our minutes and minutes cancels out. Okay, so we end up getting 0.012 liters. Okay, divided by, this is still here, so we're going to do 0.4. Okay, and this one is still here as 60 seconds. We end up getting 5 times 10 to the negative 4. Okay, and this is going to be in liters per second. Okay, or seconds over here, doesn't matter. Okay, S or SEC. So this here is the answer. Alright, this here is our green question of the day. Okay, please give this a try, pause the video, and then I'm going to be showing you the answers shortly. This here is the answer, 0.06 moles per liter per second for the BRO3 1-, and then 0.18 moles per liter per second for the BRO 1-.